that was given. Note here there are no units. What were the units for the volume?
Milliliters.
So it's a bit tedious, but you're going to have to write milliliters here for all of them. Or as an alternative to writing milliliters for all of them, you know what you could do if you don't want to write milliliters? I don't know. There are people who don't like to write units because it's a bit tedious. Yeah, and so normally what people do is here, where it says molarity of the standard acid, they'll put slash capital M. But here, that's only one entry, so it's just easier just to write it. The final reading of the acid burette, they can put slash or parentheses ml here. So if you put it in the heading of the column or in the heading of the row, then that's okay. You don't have to rewrite the unit over and over again. But if you start writing the unit and then get halfway through and say, I'm tired of writing units, I'm not going to write the unit anymore, then I have to deduct.
For the molarity base, is the unit also capital M?
Yes. Capital M. Capital M means moles per liter. Here, you'll probably want to write it as the heading. That way you don't have to write it over and over again. When you show sample calculation, I want to see the units. I'd like to see how the units cancel out. And then when we report an average molarity, we don't just report the molarity, the average molarity. We have to report the average molarity with what?
Standard deviation?
Not with the standard deviation. Standard deviation is 68% confidence interval. That would be the standard deviation. We need to report it with a 95% confidence interval. This is standard practice. That way you can see if the 95% confidence interval is wide, that is big, then there's a lot of uncertainty. If the 95% confidence interval is small, narrow, then there's less uncertainty. And that depends on how many trials you did. The more trials, the better. And how precise those trials are. Precise in this context means not the number of sig figs, because all of them have the same number of sig figs. Precise in this context means how well do they agree with one another. You know, they should all be exactly the same. Were they close?
Oh, Professor. For the molarity of the base units, you want us to write like the M and then NaOH?
Yeah.
Okay.
Capital M NaOH would be the units for base. Or you could write moles of NaOH per liter of NaOH solution. That would be the full unit. All right. So when we do titration, we like to know, about errors. Some errors will lead to a positive error. A positive error means we get a number bigger than what it should be. Some errors lead to a negative error. A negative error means it's smaller. Our calculation or calculated value is smaller than what it should be. And so this is an exercise in trying to figure out, is that going to lead to a positive error or a negative error? Because we want to know the direction in error. Like in physics oftentimes what they'll do is they'll take the absolute value. But if you take the absolute value, then you're missing something called the phase information. We want to know the phase information. So it's important to us, not to get rid of it. Sometimes we lose it in a math calculation. We have to figure out what it is. So if x squared is equal to 4, what is x? If x squared is equal to 4, what is x? Plus or minus 2. Well, we need to know, was it plus 2 or was it minus 2? How can you figure it out? If x squared is equal to 4, how can you figure out if that came from minus 2 times minus 2 or plus 2 times plus 2? How can you figure that out? Well, in chemistry, there are things we do to try to figure out what it was, because it makes a difference. Because, well, in chemistry, we're dealing a lot with waves. And we want to know, was it the negative amplitude or the positive amplitude of the wave that we're squaring to get back to the wave function? And so we don't like to take the absolute value of percent errors. We like to leave the percent error as a positive value or a negative value, depending on if we're high or low. That way we can get some idea of what the potential source of error is. And if we know the potential source of error, we might be able to correct it. Because it could be a systematic error. If you're systematically low every time you do it, it's different if you're high sometimes and low other times. If it's high sometimes, low other times, then that's a bit different than always high versus always low. If you're always high or always low, then that's an indication it might be systematic. It might not be random. So if it's systematic, it could be an error in technique or an error in calibration. So anyway, we have to start thinking, and so this is an exercise in this. So the end point of the titration was overshot. If you overshot the end point is when the color changed from colorless to pink. In titrations, we have two things. We have something called the end point. The end point is where the indicator changes color. And the other thing we have is something called the equivalence point. The equivalence point is when we have just the right amount of moles. In this case, moles of sodium hydroxide to equal the moles of acid that we're trying to neutralize. And phenolphthalein, unfortunately, phenolphthalein, what happens with phenolphthalein is it has to have a little bit of extra base, a little bit of extra sodium hydroxide to turn pink. And so we normally overshoot the end point, but it's such a small error that it's not so significant. But what if you overshot it by a lot? So what a lot of people do is they try to titrate it to a pink color. You don't try to titrate it to a pink color. That's very difficult because the shade of pink will vary. So, and it doesn't change much. So if you add an extra milliliter versus 10 milliliters, it kind of looks the same. You don't know how much you overshot it. But if we overshot the titration, what effect will it have on the molarity calculation? So the molarity of sodium hydroxide, we calculated based on x.xx milliliters of HCl standard solution. And then we converted this to liters. And then we converted it to moles using the concentration of the standard solution, which I forgot the concentration of standard solution. Somebody remember it or have it?
0.1050 moles of HCl.
Was that it? 1050?
Yeah.
Okay. And it was a 1-to-1 mole ratio. 1 mole of sodium hydroxide reacts with 1 mole of HCl. HCl is what we call a monoprotic acid. If HCl were diprotic acid, it would change this mole ratio. It would be 2-to-1. 2 moles of NaOH would be required to neutralize 1 mole of diprotic acid. If it's triprotic acid, it would be a 3-to-1 ratio here. And this is going to be divided by xx.xx milliliters of sodium hydroxide titrant. Titrant is the solution in the burette. And then we convert it to liters.
Is it alright for NaOH if we just put solution?
Yeah. So the endpoint of the titration was overshot, which means we added too much HCl or we added too much NaOH.
Because we added too much NaOH.
We added too much NaOH. If we add too much NaOH, that is, let's say we add an extra milliliter, but we didn't need that extra milliliter because the color changed the milliliter before. So if we had too much NaOH, what's that going to do to the molarity? It's going to lower it. And so this is what they're asking. The endpoint of the titration was overshot. The effect on the NaOH molarity will be lower than what it should be. In other words, it's going to be less concentrated than what it should be because it's pretending as if we had to add that much extra. We didn't have to add that much extra because the NaOH is actually more concentrated and it would have neutralized it before overshooting it. Is that what you guys got? Did anybody do these? Good. A drop of base was left adhering to the tip of the base burette. So it's not a drop, it's like a half a drop or less than a drop. It could be less than one drop. You need a full drop. It was stuck there. But it had already turned pink. What happens if that half a drop falls in there or we wash it in there? It's going to become even more pink, right? But the thing is, if you have a hanging drop like this, the hanging drop has already been measured out. And so this is the same as number one. This is overshooting it because we're adding too much base. We didn't have to add this extra partial drop. So if there's a hanging drop there, I just let it go in and then go back with acid. In Chem 1A, it might be stuck. The Chem 1A, we can't reverse this. We have to just toss it and start over again. So when you overshoot, it's a big disappointment because all that work and you don't get any results. You have to discard it into the waste and go back to square one. And so, number two, what you choose? Lower than it should be. The concentration is lower than it should be. Required less sodium hydroxide, not more. Three, some drops of acid were left clinging to the walls of the flask. So let's say you didn't have this half drop or whatever, partial drop suspended. It's good. It's good. And then you titrate it to the pink color here, but there's some acid here stuck from splatter. Let's say it splattered earlier, acid splattered onto the inside wall here, but you never washed it in. Okay, so you titrated to pink here and you got acid stuck here. What if now you decide to wash it in? What's that going to do? Well, assuming that you got this pink within a half a drop, this splatter here being washed in here is going to convert this back into colorless. If you did it correctly, but you didn't do it correctly because you left that acid there and you thought you were done. But you weren't actually done, right? In other words, you rather than overshoot the endpoint, you undershot the endpoint. Does that make sense? So if you undershot it, it should have required more sodium hydroxide. And therefore, what that's going to mean is this. If you undershot it, it's going to appear more concentrated than it really is. It's going to appear more concentrated than it really is because you should have had to add more. You thought you had already neutralized all of it, but you didn't neutralize all of it. And so you're thinking this is more potent than it really is, but it isn't because you missed the splatter here. And so that means the sodium hydroxide is going to appear more concentrated than it really is. And therefore, the effect on the molarity, it's going to be higher than what it should be. All right, so those are the two errors, high error and low error. All right, let's look at number 4. You obtain standard solution, acid solution in a wet beaker. If you obtain standard acid solution in a wet beaker, you've destroyed the standard acid. Why? Yeah, you diluted it, and the whole purpose of a standard is to know the concentration as accurately and as precisely as possible. So now you don't know, because you don't know how much water was added. And so you no longer know this concentration. This concentration is so important, 1050. If you got the acid in a wet beaker, is it still going to be 1050? No, it's going to screw up your calculation now. And so we never do it. But didn't we add water here? Yeah, we added water here, but this is standard. So we meter it out. We know exactly how much acid's in there. So now it doesn't matter. We can add as much water as we want. We know how many moles of acid we put in the flask. Adding water is not going to change it. And so what's the error?
Is it going to be higher? Because technically not only did we dilute it, but also we raised, technically it has a larger volume, I guess.
You would measure more than you actually put in.
Yeah.
Because it's no longer.
You'd measure more than you put in?
Because there's like water.
Yeah, because there's water.
It might not be a lot, but there is.
You measure more what, acid or base?
Acid.
Acid? Which would impact the base in what way?
Oh, you'd have to put more base. I don't know. You'd have to put in more base because there'd be less acid than you measured. Right?
I'm trying to.
Yeah, because it says if you measure like this much base and this much acid, but it turns out that acid has more volume, so there's like less.
So
can
you
say
over,
okay.
okay.
All right, so think about it and then convince me that you're correct.
So you need like this much acid and this much base, right? But there's water in the acid, right? So there's only actually this much acid instead of this. So you still need the same amount of base, but you have more base.
Okay. I don't know how to say it, but I get it.
You got it?
I can't.
So is it going to result in a higher or lower concentration than what it should be?
Lower.
It's going to result in a lower concentration? Do you all agree with that? Are there any people who disagree? It's good to have disagreement, you know. That way, if everybody agrees, I guess that's the consensus. So. But you know, in science, you don't want just consensus. You want an argument. You know why it should do that.
Yeah, this ends up being the
So
water.
basically, this is how much.
So
So you need this much base for this. So this is how much.
So we think the acid is 1050, but the acid is actually lower than 1050.
The base would match remove the acid because it's acid in water. So it'd be
Mhm.
less of a-
It would be like if the molarity was lower, then you would need less base. And if there's less base, then when you do the equation, you would have a higher molarity for the base, right? You'd overshoot it.
Okay. And so you say the acid will impact the base so that the base concentration is higher than what you expect. Okay, that makes sense.
So I think this is.
If you're doing this and you think it's 1050, but it's actually lower, it's going to take less base to neutralize it. And since it takes less base to neutralize it, and you're not really neutralizing all of it, you're really undershooting. Is that correct? Undershooting the endpoint, and therefore it's going to be higher. Does that make sense? Yeah, you're using less base. If this weren't diluted, you'd have to add more base. And if you had to add more base, then its concentration would be lower than adding less base. Okay, that makes sense. So we're going to say the concentration is higher than expected. All right. 5, you use the wet flask for the titration. Yeah, that doesn't matter. It's using a wet flask here is not going to change how much acid, how much base, or the concentration of the standard. And so it's not going to impact it. In Chem 1B, you do something called a pH titration. And when you add water, what it does is it changes the pH. And so it could screw up your pH titration. But in Chem 4 and Chem 1A, it won't because we don't monitor the pH. And the pH will depend on the concentration, and the concentration depends on how much water you dump into this flask. You added 4 drops instead of 2 drops of phenolphthalein. And so I told you what phenolphthalein is. Phenolphthalein is a dye, but it's an acid. And in acid, the dye is pink. Or no, that's wrong. In acid, the dye is colorless. So in order to convert the phenolphthalein from colorless to pink, we have to neutralize it with base. And so the base will react with both the acid HCl that was in here and the phenolphthalein. So this is why I say don't add too much phenolphthalein, because adding too much phenolphthalein will cause you to do what? Overshoot or undershoot? Overshoot. You're going to have to add more. So the more phenolphthalein there is, the more extra sodium hydroxide you have to add to this titration. Right now, phenolphthalein is not that concentrated, so it's not like a drop for a drop. That is, if you add 1 drop of phenolphthalein, it doesn't necessarily take 1 drop of sodium hydroxide to convert it to paint. It can take less than that, depending on the concentrations. And so the error is not that significant here. But whatever you do in the titration, you want to do it systematically. And therefore, you don't want to vary the number of drops. If you add 2 drops, always add 2 drops. Usually I just do 1 drop. 1 drop is enough to see the color. And then there's less error associated with that. Okay, so if you add 4 drops, then you need to add a little bit more sodium hydroxide, which means you're going to overshoot it, which means the concentration is going to be higher, lower, or no impact. Yeah. concentration will be lower. We didn't really have to add as much. Okay, were those clear for that? Well, since we did those, you can turn those in as well. Yeah. Since I have the extra calculations in there, you can turn this in next week too. Yeah. It's fun. Experiment 6 and 7, I see that not everybody's clear about what I want for experiment 6 and 7. For experiment 6 and 7, you know the three equations, the CE, the IE, and the NIE. There's different names for that. CE, IE, and NIE are just the names, the abbreviations, acronym I use. Our book uses a different NIE is the same, all of them, but the book uses different, and this worksheet uses different one. This worksheet is the full formula equation, which I call the complete equation, and the total ionic equation, which I call the ionic equation, and the net ionic equation. So the CE, IE, and the NIE. This is from the supplement here. And so a lot of these are double replacement. This is single replacement here. And this is a mix of single replacement and double replacement reactions. That's what we're going to do here. Potassium is added to water. Potassium added to water, that's single replacement. If we write water like this. If I write water like this, then this is A, potassium, plus water. This is my BX. Where B is going to be the hydrogen ion, X is going to be hydroxide. So hydrogen hydroxide. Water is not ionic, but I'm going to just treat it as a BX for this. And so I'll make potassium hydroxide and hydrogen. Hydrogen chloride is bubbled through aqueous lead 2 acetate. So HCl, this is a gas plus lead 2 acetate, PbC2H3O2, aqueous. This is AB plus CD. And so I just want it for a single replacement, the A plus BX pattern, and double replacement, the AB plus CD. If it's not one of these, if it's a decomposition or dehydration reaction or whatever, you don't have to do this. Just for those. So make sure you get the equation. This is NIE. Ammonia I didn't talk about, and so that's why I skipped these here. I'll talk about ammonia later. And so ammonia doesn't fit either of these patterns. So one of the reactions that you had was this. It was like copper sulfate in aqueous plus ammonia aqueous. Ammonia is very polar. It's trigonal pyramidal structure. It likes water. So ammonia dissolves in water quite readily. But we don't split it up like this. You know? In other words, we don't do hydrogen amide in H2. We don't do that like we did here for water. we get potassium plus hydrogen hydroxide, called water hydrogen hydroxide. Then it fits the pattern. We aren't going to do it here. And so this is not an A plus BX, nor it is an AB plus CD. And so skip this. The ones with aqueous ammonia skip. For special cases, we might have this hydrogen amide, like hydrogen hydroxide, when we're reacting this with very reactive metals in a single replacement sense. Then it might happen. Okay, any other questions? Yeah. The way the homework is graded is, did I assign all blue problems?
For the most part, but there's several that weren't.
And then I think chapter 6 is almost done.
Yeah, so.
Yeah, okay. For the most part, I assign blue problems. If you get stuck on a blue problem, what should you do?
Look in the back and pass the solution.
Yeah, look in the back, and if you don't get it, just write it down. You know, that's the process. You know, they say, you've heard the cliche, fake it until you make it. You know, eventually it'll click. You know, you just keep writing it down, and then your brain does things. You don't actively have to do things. Your brain's trying to figure things out. And it's passive. And so when they say that you make it, your brain's finally figured it out and it's clicked all together. And so this is why some instructors say no, they don't want any solutions manual because they think the learning process involves the struggle. But I don't think that works for everything. I think when you're learning something new, you need exposure to a lot of problems, a lot of problem-solving methods. And if that means copying down the answer, then copy down the answer. If you copy down the answer, you'll get full credit for that. However, if you leave it blank, you get a deduction. And the deduction is just a percentage. You know, it depends on how many blank ones I see or how many blank ones I figure out. So if you leave half of them blank, you're going to get 50%. You know, let's say it's one of the black problems, not one of the blue problems. Well, the black and blue problems are paired, and so they should be similar. So if you're looking at number 20, you're stuck there, then either 21 or 19 is going to be very similar to it. And so you can just try it. You don't have to get the answer to get full credit. If you just show some attempt at it, then I'll give you full credit there. Don't leave it blank with a question mark. If you leave it blank with a question mark, then I'm not sure how much work or effort you put in, but just write something down. If you write something down, I'll give you full credit. Or whether you have the final answer or not. And so hopefully then you can get full credit on the homework. Should be good. I did get a question about late homework. I do accept late homework, but there's a late penalty associated with it. The late homework you just turn in with the final. Late homework has to be complete. Where did we leave off last time? Molar volume? Was I working on a problem?
Mhm.
Well, I think I was in the middle of a problem, right? I didn't quite finish it. What problem was that? The number?
33.
33. Okay. So let's finish up that problem. Here. So then in the FES2 is, what's the common name for FES2? Pyrite, yeah, or fool's gold. But how would you name this? You know, it's an ionic compound, so, you know, sulfide is usually what charge? Sulfide is usually -2, and I have 2 of them, so that means iron must be +4. Have you heard of iron +4? No, that's a very unusual charge for iron. It's not that iron +4 can't happen. When I was at UCLA, I tried to make an iron +4 compound. I devoted a lot of work to making it. Almost had it. I think I had it, but ended up destroying it. Because it's so unstable, it reacted immediately with air and moisture fizzled out. But anyway, going back to this, it's not iron +4 because this is not sulfide. What's the anion called here? And so what is peroxide? What did you guys think of the quiz, the nomenclature quiz? Did everybody took it? It was okay, hopefully. But one of those was peroxide. Peroxide is O2 2-. And so we have these 2 oxygens. Oxygen doesn't like to bond to one another. But it looks like this. And rather than 2 oxides, if this were 2 oxides, the total charge on 2 oxides would be -4. But this is peroxide, and the total charge on peroxide is -2 versus 2 oxides. 2 oxides would be like this. This is -2 formal charge, -2 formal charge here. Sulfur does the same thing, but we don't call it per sulfide, you know? And so this is the exact same thing as peroxide. But why do they don't call it per sulfide? It would kind of make sense to call it per sulfide because it forms a structure just like this. In which each sulfur is -1 rather than -2, versus 2 sulfides. 2 sulfides, each sulfide would be -2 itself, etc. So this is called peroxide. You know what they call this anion? This is not one I had you memorize, but the name on this is so easy to memorize, but it's so confusing. It's easy to memorize, but it's confusing because this is called disulfide ion. But disulfide does not mean you have 2 sulfides. Disulfide means you have 1 disulfide, just like you have 1 peroxide, not 2 oxides. And so in one way it's easier, in another way it's more complicated because of that potential confusion there. And so another name for this is iron disulfide. It'd be iron, what would the charge on iron be? It's either going to be iron 2 disulfide or iron 3 disulfide. Iron 2. That's iron 2 disulfide. If you do geology, then you know fool's gold. You also know this one, Fe3O4. This is a black solid. Have you heard of Fe3O4 before? It has a common name. Most people know it by its common name. Do you know the common name for Fe3O4? Magnetite. Magnetite. What's the charge on iron? This is magnetite. These are nice crystals of magnetite here. A magnetite is magnetic, and so all these crystals are magnetic. You have your magnetite powder, and you take some iron, all the magnetite sticks to it. So if you go to the beach, sometimes you can find magnetite in there. You bring a magnet and then wrap it around at the beach, like river beach sand. And then you get little tiny crystals of magnetite. I've done that many times. Probably the beaches here, all the magnetite's been washed away. This is a chunk of magnetite. And these are iron nails. Very interesting magnetic properties on the ferromagnetic material. Okay, this is not peroxide. You know what this is? These are 4 oxides. So if those are 4 oxides, what's the charge on iron? Okay, if it's +2, if I have 4 oxides, do you remember doing this stuff? If I have 4 oxides, each oxide's -2, and that's going to give us -8. And then I have 3 irons. The 3 irons have to add up to +8 because this whole thing is 0, neutral charge. So I have +8 minus plus a -8. And therefore each iron has to be if they're +2, does it add up?
No.
If they're all +2, it adds up to +6, which is not +8.
Absolutely.
This is where the little trick doesn't work. Remember the little trick here? Iron +4, oxide -3. Oxide's not -3. The little trick doesn't work. It's a little rule. Violations of that. So that's not going to work. So this is why you want to expose yourself. If you expose yourself to a lot of problems, then, if you're in a small box all the time, you're just focusing on one problem, then you have like the blinders on. You know what I mean? So a lot of instructors will say, just focus on one problem. If you don't get it, don't give up. Keep working on it. Well, that my personal experience is some problems, I'm there 1 hour. I haven't gotten it. 2 hours, I still don't get it. 3 hours, nothing's clicking. What should you do? If you've already wasted 3 hours on one problem, is that a very effective use of your time? No, in fact, it's a waste of time. It's good because what's going to happen is those 3 hours are going to be banked by your subconscious. And even though you aren't going to be working on that problem continuously, your subconscious is still working on the problem. It's kind of weird. And then eventually things click. And then you go, oh yeah, that's how you do it. But the problem is will it click in time for the test? Sometimes yes, sometimes no. Depends on how early you start. And so I told you about the time I was after the final exam at UCLA. Did I tell you that? Was it Ralph's? And then I was waiting in the checkout line. It was like 10 or 15 minutes. The Ralph's is right across the street from school there. And when Ralph, it's like 15 minutes later, right after the final, and then it clicked, the problem. But it was too late. And so the more, the more variety you see, the wider your horizons will be in terms of problem solving. And so this is actually very simple. And when you see it, you go, that was so simple. What is it? Maybe you already figured it out. Did you? Figure it out?
Figured out this.
Mm-hmm. The charge on the iron?
Unless you want to do decimals.
The thing is, all the compounds that you've seen all have the same charge on it. But this is so simple. You know what this is? 2 irons are 3 plus, and 1 iron is 2 plus. So 3 plus 3 plus 2, 8. And so this is what we call mixed cation salt. If you've seen this before, then it's quick. It's easy because I've seen that before. But if you've never seen that before, then you might figure it out, you might not. And so that's why I don't care if you write down the answer. At least you're seeing something. Hopefully you're not just, what some people do is, I said that I don't care if you write down the answer. So what some people have done is they've just taken a picture of the solutions and then handed that in for their homework. They didn't even look at it. They didn't even want to write it down because they didn't want to waste the time writing it down. So they took a picture of this answer key and then handed that in as their homework. But I think at the bare minimum, you should write it down. So this is why I say just at least write it down so it logs into your subconscious. And hopefully that proves useful in the future. So that's my philosophy on homework. And with that philosophy, that means everybody should be able to get 100% on the homework. Unless it's late, and then there's a late penalty.
I have a question.
Mm-hmm.
How would you name, what would be the ionic name for Fe3O4?
This one brings up a failure for the nomenclature rule. It's a rule, it's not a law. Right? And so because of failures like this, there is a proposal to change the rules for naming ionic compounds. Because naming ionic compounds will fail here. And so what they want to do is they want to change the name for this to the binary molecular compound style. And so the way they propose the name for this is they propose tri-iron tetroxide. So tri-iron tetroxide. Tri-iron tetroxide, you'll never get the formula wrong. 3 irons, 4 oxygens. Otherwise, how do you name this? You could name it iron 3, iron 2, oxide, but then, in this case, there's only 1 ratio. If you had iron 3, you're going to have, are you? Yeah, to get an even number, you'd have to have 2 iron for every 2 iron 3s for every iron 2. So you may be able to figure it out. However, there comes a problem when we're looking at things like this. Phosphate is a 3 minus. And what we could have is we could have a mix of sodium, potassium, phosphate. If I had sodium, potassium, phosphate, or potassium sodium phosphate, how many sodiums and how many potassiums do I have? I don't know. You know, because I could have 1 sodium, 2 potassiums, or 2 sodiums, 1 potassium. And so this is not descriptive enough. And so it depends on the ratio of sodium to potassiums. If it's like this, then we could call it, you know, sodium dipotassium phosphate, something like that. And so we have to start using composite rules, or we have to use, you know, an alternate set of rules to name those, because our rules will fail us for that. So why don't we just switch everything to this? So there's a debate about these things. And the debate is taking place by the International Union of Pure and Applied Chemistry, called IUPAC. And so IUPAC sets these rules that people try to adhere to, including us. Although a lot of IUPAC rules we don't pay any attention to. They're too cumbersome, so we just use our names. And so they do nomenclature here. IUPAC. And so they have a bunch of recommendations. Interdivisional Committee on Terminology, Nomenclature, and Symbols. You know, there's already disagreement. You know, disagreement is, should we call it aluminum or should we call it alumininium, whatever, you know.
What does the other one mean?
Aluminum.
It's basically the same thing.
Yeah, it's the
Like some weird English just have certain.
it depends. Like aluminum versus aluminium. English speakers of North America use aluminum. So here in North America, we use aluminum. Aluminium is used everywhere else. So IUPAC is trying to get everybody to use the same name. But Americans are kind of stubborn, so we're going to continue using aluminum, probably forever.
For marketing.
Yeah, and aluminium is hard to pronounce unless you're British English or something like that. Then they have a very nice pronunciation of it. Why do British say aluminium? Well, nomenclature, you see variations of how things are named. And so they're just rules. We try to just follow the rules. For our test, we just try to follow our rules. That's it. All right, so that was talking about nomenclature. What were we on? We were on this 33. So how would we name this? We don't name this using any of our rules. So that's one of the exceptions to our rules. That's okay. Magnetite was shown in an earlier homework problem, and they just called it magnetite. They didn't try to name it. This one they might just call pyrite or iron 4. So how far did we get in this particular problem?
We're pretty much almost done after we got back to work.
Okay, so there are a number of ways we could solve this particular problem, depending on what we want to do with the SO2. All right, so here we have the 4 FeS2s solid plus 11 O2 gas. So we're burning the pyrite. When we burn the pyrite, we're going to form 2 Fe2O3. Fe2O3 is named using our standard ionic nomenclature. What's it called? Fe2O3? This is on the quiz, wasn't it? I hope you guys got it right. You call it rust, but iron 3 oxide would be its correct name. Did you get it? Oh, you didn't?
Oh, no, wait,
You got it?
yeah,
Okay.
we're good. I thought it was okay, yeah.
All right.
I think I might have forgot. I might have said iron. I didn't say iron, please say it. Okay, if I
Okay.
put iron.
You used iron?
And I put parentheses.
You put iron in parentheses?
For iron parentheses, forget about the Roman numeral.
Did you write iron 2 or iron 3?
Possibly, I'm not 100% sure, but unfortunately I'm leaning towards I put 2
Okay.
on it.
Yeah, here the little trick works. Iron 3, oxygen would be 2 minus. So this is iron 3. Over here, this is actually iron 2. Disulfide. And disulfide does not mean 2 sulfides. This is a disulfide ion. And so this would be named as ionic compound. It's just you didn't learn this anion. So what happens, we're going from iron 2 to iron 3. So the oxygen is oxidizing the iron, but the oxygen is also oxidizing sulfur because we're going from sulfur -1 to sulfur +4. And so this is kind of an interesting redox reaction because we're oxidizing both the sulfur, which is easier to oxidize than iron. We're oxidizing the sulfur to generate that. When we burn sulfur, we make oxides of sulfur, like sulfur dioxide. And that sulfur dioxide is used to make sulfuric acid. So sulfur dioxide is used in making sulfuric acid, which comes from sulfide ores by roasting. So we roast the pyrite. And the sulfuric acid is used for lots of applications. So we're going to go from grams of FeS2, 598 grams, and then we're going to go to moles of FeS2. And then we're going to go to moles of SO2. Okay, but we're not going to grams of SO2. What we want to do is we want to go to liters of SO2 gas. Now, there are different routes we can go. If this is STP, did you memorize the STP number? No. I you know what? Don't memorize it.
Like it's
Um,
something 0.77.
Yeah, there are actually 2 STP numbers to memorize. There's STP at 1 bar. STP at 1 bar is 22.7.
Okay.
And then we have STP at 1 atmosphere, which is 22.4. STP at 1 atmosphere is what I had memorized as a student.
And you said that you shouldn't have memorize that?
You shouldn't memorize it, but I hate if it would come onto a test. It won't come on my test, but a standardized test. But it's not a hard number to calculate, so it's just better to calculate. Are we at STP? No, STP is, how many did you see?
0.
And how many torr? You know what STP in torr is? In bar, no, I don't have that. I'd have to calculate it. In atmosphere, I do. If it's atmospheres, it's 760. So it's 0 degrees C, 760. That would be 22.4. But in bar, I don't have that memorized, but I don't want to memorize a whole bunch of different STPs. Right? One for bar, one for atmospheres. But we're not even there. Are we at RTP? Room temperature? This one is more useful to memorize because we do most of our reactions at what temperature? Room temperature. And if you look at these tables, a lot of these tables are at room temperature, although these ones don't say it. And so this one's useful to memorize. Do you have it memorized, RTP? You don't really have to memorize it, but it's 24.5 liters per mole. This is useful to memorize because it's about 25 liters per mole. And we do a lot of reactions at room temperature and 1 atmosphere pressure. But we're not at RTP, so we're not going to do that. In fact, we're at this temperature and this pressure. And so what we can do is we can calculate the molar volume at that. In fact, these are all molar volumes. And so we don't have to memorize any of them if you know how to calculate the molar volume. The molar volume, what's the equation for molar volume? A lot of people have the equation for molar volume memorized if you're doing gas stoichiometry because it's just a handy number to have. And the equation for molar volume is
RT over P.
RT over P. If you ever forget it, then we just need the units to figure it out because the units are going to tell us. The units of R are what? Liters times atmosphere divided by mole times Kelvin. The units for T? Kelvin. The units for P? Atmospheres. And so does this work out? Atmospheres cancel, Kelvin cancels, and that leaves us with liters per mole. Well, that's molar volume. Molar volume is liters per mole. And so did we already calculate the molar volume under these conditions? What did it come out to? 30?
30.897.
30.897 liters per mole. All right, so we're going to do the calculation using molar volume, and then we're going to use the calculation using the ideal gas law. And so using the ideal gas law, we're trying to figure out the volume. Volume is equal to nRT over P. And so we can either use the molar volume and use that as a conversion factor, or we can stop here and then plug everything in to the ideal gas law to end up with the volume of SO2. The volume of SO2 is going to depend on the temperature. The higher the temperature, the greater the volume. And the pressure, the higher the pressure, the smaller the volume. So, you have different effects. And so let's look at calculation 1 first. Did I set up calculation 1 already? Did we already finish it? No? All right. So it's going to be 598 grams of FeS2. So when you don't know the name, you just read out FeS2. That's fine. People do that all the time. If you don't know the name of it, just call it FeS2. What was the molar mass of FeS2? So this is homework. Homework, calculating molar masses becomes a bit tedious. You're going to have to calculate on tests usually, but in the homework, what we can do is we can just look it up. That'll save time. This is fool's gold here. It does look like gold. Nice. This is not the structure. You gotta watch out with stuff you find on the internet. This is not the structure at all. This is the structure of FES2 here, or here, or here. But anyway, I want the molar mass. So let's look at the molar mass here. 119.98 grams per mole. So 1 mole of FeS2, 119.98 grams. And then we're going to convert it to moles of SO2. So there's 8 moles of SO2 for every 4 moles of FeS2. So that cancels out moles of FeS2, and then we have moles of SO2. And here we're going to use the molar volume, but I need to invert it, or no, I don't need to invert it, I'll just use it as is. If I use it as is, it's 30.897. This is more sig figs than I'm allowed. I'm only allowed 3 sig figs, so this is going to be 30.897 liters per mole. And I have 3 sig figs here. I'll just carry some extra digits to minimize. This is for gas. And so how many liters of SO2 gas do I have? $598 divided by 119.98 times 8 divided by 4 times 30.897. $307.9 liters of SO2, which we're going to just round to 308 liters of SO2 gas. It's really important that SO2 is a gas. If SO2 is a liquid, this doesn't work. You know, because this is a molar volume of not a liquid, this is a molar volume of a gas. All right, that's method 1, using the molar volume. I prefer the molar volume method sometimes, because in method 2, what we're going to do is we're going to first calculate the moles of SO2 and then plug that into the ideal gas law here. And so method 2, we would do 598 grams of FeS2, convert that to moles. 1 mole of FeS2 per 119.98 grams of FeS2. Then we have 8 moles of SO2 for every 4 moles of FeS2. And then we stop here and we calculate how many moles of SO2 we have. So that's going to be 598 divided by 119.98 times 8 divided by 4. And so that gives me 9.968 mole of SO2. Okay, then we want the volume of SO2. Since SO2 is a gas, we're going to use the ideal gas law. The volume of SO2 is the mole of SO2 times R times the temperature of the SO2 divided by the pressure of the SO2. So the moles of SO2 is 9.968 moles of SO2 times R, 0.08206 liters times atmosphere per mole Kelvin. I'm running out of room here. Times T. And so I need to convert the temperature to Kelvin. What was the temperature in Kelvin? 4 something? 489 was it? $487. Let's do this. Hopefully I can do this in 214 plus 273. So 487. The temperature in Kelvin is 487 Kelvin divided by the pressure of the SO2. Pressure of the SO2 is 983 torr. So we'll plug that in, 983 torr, and then convert that to atmospheres. So 1 atmosphere per 760 torr. So the moles cancel, atmospheres cancel, Kelvin cancels, and torr cancels. That leaves me with liters. That's what I want, liters here. And so 9.968, I left all the digits in my calculator, times 0.08206 times 487 divided by 983 times 760. And I get 307.9 liters of SO2, which is going to equal 308 liters of SO2. Both of these should give you the same answer within rounding. And so your book does it by 4 methods. 1, STP. Your book doesn't use RTP. 2, molar volume. 3, ideal gas law. What's the 4th method? The 4th method is a straight liter to liter conversion. And actually, that's the easiest one to do. The stoichiometry gets very easy if both of them are gases and they're both at the same temperature and pressure. And so let's take a look at a liter to liter conversion here. Called volume to volume gas stoichiometry. And so we're going to do number 41. Number 41, sulfur burns to SO2. So over here I burned sulfide. Sulfide burned to SO2, but also sulfur burns to SO2. It's not as rich of a fuel. Sulfide is a much better fuel because it has more electrons. Fuels have electrons that they can give to the oxidizer. And so this is going to form sulfur dioxide. And when I look at this, this is already balanced. Sulfur is a solid, O2 is a gas, SO2 is a gas. When this burns, the flame is very interesting here. The flame gives off this light. So sulfur burns in SO2 with a beautiful deep blue-purple flame. So this is the deep blue-purple flame. But with a foul, suffocating odor, SO2 is toxic. But if SO2 is toxic, you've seen SO2 before. Where did you see SO2 before? You remember seeing SO2 before? Except they, SO2 is called sulfur dioxide, but they didn't call it sulfur dioxide because sulfur dioxide is kind of, if you think about sulfur dioxide, you think, oh, that's foul smelling, suffocating odor, toxic.
It's in the water.
It's in the wine, right? They call it sulfite. Sulfite is much more obnoxious. So if somebody Googles sulfur dioxide and they thought, oh, they're putting sulfur dioxide in wine, I don't want to drink that. Foul, toxic, suffocating. Sulfur dioxide can be burned further because sulfur dioxide is a reducing agent. And so it's an antioxidant. And so it can be burned further. It's not completely combusted. You know what sulfur dioxide can burn all the way to?
Nothingness? I said nothingness.
Yeah, burn to nothing.
I mean, it burns in the sun.
Yeah, I mean, that's what people used to think. It burns and just disappears. And then there was a theory or hypothesis. The hypothesis is that some kind of like, they turn into spirits of the element. Those spirits of the element disappear into the ether.
Interesting.
Yeah, it's pretty interesting. And it wasn't until Lavoisier started doing experiments that he realized that they don't really disappear into the ether. They're still there. And so it doesn't burn to nothing. It burns into
Just
Sulfur trioxide.
sulfur trioxide. How about sulfur tetroxide? Could it burn to sulfur tetroxide? No. But you might say, didn't we have sulfur tetroxide before? Isn't sulfur tetroxide also known as sulfate? Isn't that sulfur tetroxide? No, this is not sulfur tetroxide. Sulfur tetroxide would be neutral and sulfur would be plus what? This is not peroxide, this is oxide. This is 4 oxides. If that's 4 oxides, then sulfur's got to be plus 8. And so this is, but if this were sulfate, this is why when you do nomenclature, you don't forget the charge. If it's sulfate, sulfur tetroxide and sulfate are 2 totally different things. One wouldn't expect sulfur tetroxide to exist, but one would expect sulfate to exist. Because if it's sulfate, then sulfur is plus. So it would go like this. Minus 2 times 4 is minus 8. Minus 8 plus what gives us minus 2? So minus 8 plus 6 gives us minus 2. And so this is sulfur in the plus 6, but this would be sulfur in the plus 8. Now, that doesn't mean you can't form more exotic species. So sometimes the students will just Google SO4. They have sulfate. Sulfate. We only get sulfate. Here, I don't know why they're not writing the charge. They need to write the charge. Okay. All right, so just going back, this burns nicely. Sulfur is kind of a big atom. It being a big atom, it's easier to oxidize than a small atom. Something like this. Let's see what the question's asking. How many liters of O2 are needed to form 35.2 liters of SO2? Both gases being measured at 741 torr and 26 degrees C. So I want to make 35.2 liters of SO2. So 35.2 liters of SO2 gas. And so to go from liters to moles, I need to use the, well, there are different ways we could do this. We could use the molar volume at STP. We could use the molar volume at RTP, or we could just use the molar volume at any temperature and pressure, or we could use the ideal gas law. Ideal gas law is the number of moles is equal to PV over RT. And then I'll get moles of SO2. Once I get moles of SO2, then I can go and get moles. What are we asking for here? O2. And then from moles of O2, I can get volume of O2, or liters of O2, gas. And here it's the same thing, molar volume, RTP, STP, RTP, is molar volume, any temperature and pressure, or ideal gas law. Ideal gas law we solve for V. V equals nRT over P. But if the gases are both at the same temperature and pressure, which they are, then we can bypass this altogether. If the gases are at the same temperature and pressure, we could just use the volume ratio. The volume ratio is equal to the mole ratio at constant T and P. So the mole ratio is like this: 1 mole of sulfur, 1 mole of O2 produces 1 mole of SO2. The volume ratios for gases. And so we can also say 1 liter of O2 is going to produce 1 liter of SO2, but it's not going to be 1 liter of sulfur. And so the volume ratio, it just works for the gases if the gases are at the same temperature and pressure. Sulfur is a solid, it's not a gas. And so the volume ratio does not work here. The mole ratio always works. And that's why we express equations in terms of mole ratio, but the volume ratio doesn't. So we don't have to do all this work. If I have 35.2 liters of SO2, then I need 35.2 liters of O2. And so the answer is 35.2 liters because it's a 1-to-1 volume ratio. But it doesn't mean I need 35.2 liters of sulfur because sulfur is a solid. In fact, we'll need a lot less because solids are much more dense. Gases are 1,000 times less dense. And so A is simple. What if only SO2 is at those conditions, but O2 is at 17 degrees C, 847 torr? Now this is a problem. This volume ratio works at constant temperature and pressure, but if one of the gases has one set of temperature and pressure, and the other gas has a different set of temperature and pressure, then this doesn't work. Because, as the temperature changes, gas can expand or contract with different temperatures. And the same thing with at different pressures. At high pressures, gases contract. At low pressures, gases expand. And so it's going to depend on the pressure. And so what we do here is, do you like the molar volume method or do you like the ideal gas law method? And I recommend just picking one and just sticking with it. Which one do you prefer? This is part A. This is part B. You like the molar volume or the ideal gas? Okay, molar volume. Then let's do using the molar volume method. So when we're at different temperatures and pressures, then the molar volume for this step is not the same as the molar volume for this step. We're going to have two different molar volumes, and neither molar volume is at STP or RTP. And so we're going to have to calculate these individually, separately. And so it's a bit of a pain. Let's go ahead and do that here. So the molar volume of the SO2 gas is equal to RT over P for the SO2. So the SO2 is measured at 741 torr, 26 degrees C. So R is 0.08206 liters atmosphere per mole Kelvin. T is 26 plus 273, 299, 299 Kelvin. P is 741 torr. And we're going to convert that to atmospheres. 1 atmosphere is exactly 760 torr. Torr is the same thing as millimeter of mercury. And so the torr cancel, the atmospheres cancel, the Kelvin cancels, and that gives us liters per mole. And so the molar volume for SO2 under these conditions, we go ahead and calculate that. It's 0.08206 times 299 divided by 741 times 760. 25.165. We're only allowed 3 sig figs because of the, so 25.1, and I'll carry 1 extra. 25.16 liters per mole. That's the molar volume of SO2. Now, the molar volume of the O2 is going to be different because they're collecting the O2 under different conditions. And so the O2 is going to be collected at 17 degrees C and 847 torr. And so we're going to calculate the molar volume of the O2, RT over P. This is going to be 0.08206 liters atmosphere per mole Kelvin. And the temperature is going to be 17 plus 273, which would be 283, plus 7 would be 290. So this is going to be 290 Kelvin. Divided by the pressure is 847 torr. 847 torr converted to atmospheres. They'd like to use torr. Most people will write millimeters of mercury. Torr takes up less space. Now, millimeters of mercury would be mm space Hg. That's 5 character spaces. This is only 4. So did you get 21.35 liters per mole? So why is it smaller? You know why it's smaller? 1, lower temperature. Lower temperature, gases shrink. 2, higher pressure. Higher pressure, gases shrink. So it's going to be smaller. And so now we have our conversion factors, and so we can just do this using dimensional analysis. 35.2 liters of SO2. And then we're going to use the SO2 molar volume. that is 1 mole of SO2 is going to occupy 25.16 liters. This is MB for SO2. And so the liters of SO2 cancel, and that gives us moles of SO2. And then from moles of SO2, we'll go to moles of O2. It's a 1-to-1 mole ratio. So 1 mole of O2 for every 1 mole of SO2. And that cancels the SO2. And then we have the molar volume for O2. The molar volume for O2 is 21.35 liters per mole. This is just for O2. And so the moles of O2 cancel, and that leaves us with liters of O2. So let's see what we end up with here. 35.2 divided by 25.16 times 21.35. This is going to give us 29.86 liters of O2 under those conditions. To 3 sig figs, it's going to be 29.9 liters of O2 gas. All right, so this is your basic stoichiometry type problem. But do you know how your book solves this problem? Let's take a look. Your book takes a different approach to this. And so let's take a look at number 41. Okay, so A is just a direct liter-to-liter conversion. The liter ratio is the same as the mole ratio for gases if there's no change in temperature and pressure. That's A. B, there was a change in temperature and pressure. So what is this equation here? Seen this? V2 is equal to V1 times P1 over P2 times T2 over T1. You seen that? What does that equation look like? That's the so your book didn't do it this way. You know what your book did? They did it this way. What they did was this. They went from 35.2 liters of SO2 under one set of conditions and then figured out the volume of SO2 under the new set. And so this 35.2 liters of SO2 was originally at 299 Kelvin and 741 torr. So this is at 299 Kelvin and 741 torr. What they did was they used the combined gas law to figure out what the new volume would be at 290 Kelvin and 290 Kelvin and 847 torr. So this particular calculation here is V2. V2 is equal to what? V2 is equal to P1 over P2 times T2 over T1 times V1. In other words, this equation came from P1 V1 over T1 is equal to P2 V2 over T2. And then we just solved for V2. The number of moles didn't change. The number of moles didn't change, the moles cancel out. And so V2 is equal to P1 over P2 times T2 over T1 times V1. And so they use the combined gas law to determine the volume of SO2 under oxygen's condition. Okay, once they got the volume of SO2 under oxygen's temperature and pressure, then they use the volume ratio, or the liter ratio, or the liter to liter conversion here. And so they use method A to do this, and they had to do an extra step here. And so the next step is just to do a volume to volume conversion. Yeah, so that's another way you can solve it. I prefer just doing it the stoichiometric way. You know, even though this might be a little bit shorter, or may not be. It's so small. All right, let's stop here. We'll take a break. Let's start up again. The gas mixtures continues in chapter 15. And this is Dalton's law, where it was talked about. I talked about gas mixtures in the context of Dalton's law, and what was the other law that I used? When we think about a gas mixture like air is comprised of nitrogen and oxygen. We could visualize the mixture in terms of something called a mole fraction, or Avogadro's law and Dalton's law. So Dalton's law is talked about in chapter 15. So Dalton's law deals with gas mixtures as well. So for Dalton's law, what we do is we have the volume fixed. So if I take 1 liter of nitrogen and combine that with 1 liter of oxygen, how many liters of mixture do I end up with? So if I take 1 liter of nitrogen plus 1 liter of oxygen, do I get 2 liters of mixture, or do I get 1 liter of mixture? In terms of Avogadro's law, if I take 1 liter of nitrogen plus 1 liter of oxygen, I'm going to end up with 2 liters of mixture. That's Avogadro's. But for Dalton's law, if I take 1 liter of nitrogen plus 1 liter of oxygen, I'm going to get 1 liter of mixture. So I'm going to cram all that mixture into the same size container, which is going to do what? It's going to change the pressure. And so the pressure is going to go up. And so it depends on the pressure. In this case, I have the pressure of nitrogen, 186 millimeters of mercury, and the pressure of oxygen. Now I'm going to cram everything into one container, so I'm going to have both the oxygen and nitrogen colliding with the wall. And so the combined pressure of this will be 279 millimeters of mercury. And so Dalton's law is just this. The pressure total gas mixture is equal to the sum of the partial pressures. So if I remove the nitrogen out of the mixture, and there's no oxygen in here, that's 186. If I remove the oxygen out of it, that's 93. So 186 plus 93 gives us the total pressure. The total pressure is generated when both nitrogen and oxygen collide with the container. Now this is kind of weird because it doesn't look like 1 liter. It looks like the volume is changing here because of this. You see, this is not really 1 liter, 1 liter, 1 liter because of this is different than this, which is different than this. So this is an error here, but we'll just pretend it's 1 liter, 1 liter, 1 liter. Dalton's law is even simpler than that. And so let's take a look at a simple Dalton's law problem. And the Dalton's law problem is like this. The total pressure is equal to the sum of the partial pressures. So it depends on how many gases. If we have 3 gases, then we just add them up, P1 plus P2 plus P3. And so the combined collisions or the combined pressures of all the gases present in the mixture. So when we're doing the Dalton's law problem, oh shoot, it's gone. So when you look at it, it seems pretty straightforward. So if a gas mixture, the partial pressure of methane is 154 torr, of ethane is 178 torr, and of propane is 449 torr. Find the total pressure. So the total pressure is if all these gases are in the mixture, the total pressure will be the combined pressures, the sum of the partial pressures. This is going to be 154 plus 178 plus 449, which gives 781 torr. So that's Dalton's law of partial pressures. So we just added the partial pressures. A scientist sets up an artificial atmosphere with 4 gases. Their partial pressures are 0.78 bars of nitrogen, 0.21 bars of oxygen, 0.009 bars of argon, and 0.025 bars of water. Water is not liquid here. Water would be humidity, water vapor. What is the total pressure? The total pressure is you just add them up. That's it. And so in Dalton's law, the pressures are additive. In Avogadro's law, the volumes are additive. One of the biggest applications of Dalton's law is when we collect gases over water. And so this is one of the reactions we do in Chem 1A. In Chem 1A, you take potassium chlorate, KClO3, which is a white solid. And you'll take some potassium chlorate, weigh it out into the test tube here. And then you're going to add some black powder. The black powder is manganese 4 oxide. Manganese 4 oxide is what is called a catalyst. The catalyst just speeds up the decomposition. Otherwise, the decomposition of KClO3 proceeds a little slower. So what happens is KClO3 will decompose into oxygen and KCl. The KCl stays here. The oxygen gas is bubbled. And what we can do with oxygen gas is we can capture it in this test tube. This test tube is filled with water and then inverted in here. And so as the gas is formed, it bubbles up here and collects at the top of the test tube, pushing the water out of the test tube. So you can see up here some gas is collected. Now, when we first do this, this is an Avogadro's type problem. This is an Avogadro's type problem because what happens is, as the oxygen is being generated, then what's in here is air. And so what we're doing is we're generating oxygen and combining it with the air. So the volume of the oxygen plus the volume of the air is the total volume. And so the volume is not fixed. And so what happens is whatever oxygen we generate is going to push the air out here. So if we generate, let's say, 5 milliliters, it's going to push the air, and we'll have 5 milliliters of air here, plus some oxygen. Oxygen is probably there. And so we can figure out how much gas is generated over here. Look this here. And then, but other than that, we might try to visualize this because we don't fill the whole thing with water. If we fill the whole thing with water all the way here, then whatever gas we generate is just pure oxygen. This is actually a more complex mixture than what's shown here. And so whenever we collect a gas over water, and so we're going to simplify this now. And so the KClO3 produces oxygen gas. The oxygen gas is fed through a tube and rises into an inverted test tube here. And so up here, we're going to have our oxygen gas. Well, in reality, it's not pure oxygen, there's some air in there as well, but with Avogadro's law means that any change in volume is due strictly to the oxygen being added to it. But we're going to completely ignore the air. And we're going to just call that the oxygen because that's just going to serve, whatever volume this is, that's how much oxygen we generated. But there's one more thing about this, there's not that much air in the tubes anyway. So the one other thing about this is what we call wet oxygen. It's wet oxygen because when we bubble the O2 in the water, it picks up water vapor. And the water vapor, and not only that, we'll put water vapor as blue, and then the oxygen is red. So we end up with a mixture here. of wet oxygen. Okay, now, in order to make Avogadro's work, that is, whatever oxygen we generate is going to combine with the air, we have to make sure that the oxygen generated and the air are at the same pressure. So what we do is this. Let's say we generated a large amount of oxygen. They just call it gas. We generated a large amount of gas that's wet with water vapor. What we're going to do is we're going to equalize it because initially the air is at atmospheric pressure. I'll just show you here. And so when we seal this stopper on here, this is glass, and this is usually rubber tubing. When we seal the stopper on here, it's at atmospheric pressure. It's not at higher pressure or lower pressure. It's just open to the air originally. And then we seal it so the air is trapped in here. In order to make the volumes combine, under Avogadro's law, the pressures have to be the same. And so the pressure of the air initially here has to be the same as the pressure of the gas that we collect in the tube. In order to equalize the pressures there, what we're going to do is we're going to take the tube and put it in the sink. And then we're going to look at the water level. So the water level inside the tube matches the water level outside the tube. If the two water levels are equal, then the pressure of the wet gas inside here is the same as the pressure of the atmosphere, the barometric pressure outside here. And so now we know the pressure of the wet gas, the pressure of the wet O2. Here we don't know the pressure because the pressure isn't the same. The pressure on the atmosphere outside the tube is not the same as the pressure of the weight of the wet O2. To make the two pressures the same, I'm going to put this in the sink and lower this until the two lines match. Once the two lines match, then the pressure inside and the pressure outside are the same. But that pressure is going to be the total pressure according to Dalton's law. And so we end up with the total pressure once the pressure has been equalized like that. Okay, once we have the total pressure is going to equal the pressure of the wet O2. The pressure of the wet O2 is equal to the pressure of the dry O2 plus the pressure that's generated by the water molecules hitting the walls. And that would be the pressure of the water vapor here. Okay, it turns out that we can figure out the pressure of the water vapor. If the gas is saturated with water vapor, then it is at 100% relative humidity. Are we at 100% relative humidity now? No, 100% relative humidity is very uncomfortable. If we were trapped in here, it would be probably 100% relative humidity. Yeah. But fortunately we aren't. If we're at 100% relative humidity, then that humidity depends on the temperature. Because what happens is, we're going to have water molecules vaporizing off the surface. The higher the temperature, the more water molecules evaporate. The more water molecules that evaporate, the higher the humidity here. But at the same time as the water is evaporating off the surface, there's water is condensing onto the surface. And so if a water molecule hits the surface, it could stick. If it sticks, that's called condensation. So we have evaporation and condensation occur. When we hit 100% relative humidity, what that says is that the evaporation rate is equal to the condensation rate, and the gas has been saturated with water vapor. We can't get any more water in there. It's hit a max. And the maximum amount differs depending on what the temperature is. And so we can take a look at something called the vapor pressure curve of water. And this is what it looks like. The vapor pressure of water. And this is going to be like temperature. I just want to go up to 100 degrees C. So what happens is, as we increase the temperature, we have more and more water. But the odd thing about it is it's nonlinear. And so what happens is, as the temperature increases, the humidity doesn't increase linearly, it increases exponentially. It becomes quite a bit more humid with small temperature changes up here. What this signifies is the humidity, that is the saturation level. And so at low temperatures, not much water vapor. At high temperatures, lots of water vapor. And that curve comes from data, experimental data. And so let's take a look at the data table here. It's hard to see that it's curved. This is the data table, so you just measure it. You know, how much water vapor is in the container. And it doesn't matter the size of the container. You know, big container, small container will have the same vapor pressure. It'll have different amounts of water with the same vapor pressure. So if we're at 25.0 degrees C, we get 23.756 torr of water vapor. If we bump it up to 31.0, we're at 33.695 torr of water vapor. And this would be at 100% relative humidity. And so we got to make sure that this is at 100% relative humidity. And then we can look up this number in a table. Somebody else has measured it. And so based on that, we can get the pressure of the dry O2. The pressure of the dry O2 is equal to the total pressure, which would be atmospheric pressure, minus the vapor pressure of water. Here. And so let's take a look at a typical calculation here for this. This is a typical calculation. Whenever you collect gases over water, we have to know how much water is saturating that gas. And that's going to depend on the temperature. So oxygen is generated for a laboratory experiment by bubbling the gas through water. Bubble the gas through water, it's going to saturate it with water vapor, as illustrated in figures 15.3 and 15.4. The total pressure of the oxygen saturated with water vapor, so this is what we call wet oxygen, is 755 torr. So that 755 torr are due to the collisions of the oxygen molecules and the collisions of the water molecules with the wall. And so how much of that is due to oxygen molecules? How much of that is due to water molecules? We have two unknowns. But one of the unknowns we can get from the table, that table is called the vapor pressure table. The temperature of the gas mixture is 22 degrees C. And so if we're at 22 degrees C, then we go to this table and we look. That's at 22.0. So we go to 22.0, the pressure that's generated by water when it's saturated is 19.827 torr. So we go back over here, and that's where this number came from. But they only use 3 sig figs. So they say the water vapor pressure at that temperature is 19.8 torr. What is the partial pressure of the oxygen? And so the partial pressure of oxygen, they're talking about dry oxygen. So the pressure of the wet oxygen is equal to the pressure of the water vapor plus the pressure of the dry oxygen. Therefore, the pressure of the dry oxygen is equal to the pressure of the wet oxygen, which should equal atmospheric pressure if you equalize the water levels, minus the pressure of the water vapor. So this is a typical calculation. 755 torr of wet minus the water gives us the dry. And so it's 735 torr. This is a typical calculation for that. Okay, now once we know the pressure of the dry O2, then we can figure out how many moles of O2 form. The moles of dry O2, or pure O2, is equal to the pressure of the dry O2 times the volume of the dry O2 divided by RT of the dry O2. So the pressure of the dry O2 we get from Dalton's law. What about the volume of the dry O2? Well, Dalton's law says this. Dalton's law says that the total pressure is equal to the sum of the partial pressures. As long as the temperature and volume are constant. So what was the volume of nitrogen that we had in the previous one? Let's take a look. Back here. The volume of nitrogen, 1 liter. What was the volume of oxygen? 1 liter. What was the volume of the mixture? 1 liter. So in Dalton's law, we say that the volume of the dry oxygen is equal to the volume of the wet oxygen, which is equal to the volume of the water vapor. In other words, they're all in the same container, so they all have the same volume. And so we just need to measure the volume of the wet oxygen, and the volume of the wet oxygen is the same as the volume of the dry oxygen. And then we can calculate the moles of dry oxygen. Does that make sense? All right. So there are two ways of dealing with mixtures. So we talk about Avogadro's, we talk about Dalton's, and depending on the problem, we use either, but we can't use both. So we pick one or the other. We either look at a mixture in terms of Dalton's, or we look at a mixture in terms of Avogadro's, or we look at a mixture just in terms of moles, mole fraction, that we talked about at the beginning of chapter 14. So let's take a look at a problem here dealing with mixtures. And this problem is kind of an advanced problem. I probably would have put it in the advanced section, but it's not in the back section, it's in the regular section. It's going to be number 39. Let's try number 39. And, I'm going to record that. And so let me tell you, you can handle this in different ways. There are different ways to solve number 39. You might try Dalton's like this, or you might try Avogadro's, or you might try none of them. You know. For number 39. Okay, yeah. That's the way the book does it. So we'll take a look at alternate methods as well. Is that what you did too, John?
I think I did. I just went directly from, I used Dalton's law to get the moles of the mixture, and then from the moles, I just went to the mole ratio, so I went to mole NH3, or NH4, NO3, and then converted that to grams.
Okay. Anybody else do it a different way? All right, so if we take some amount of ammonium nitrate like this, let's say 1 mole of it, and decompose it, its volume is going to expand tremendously. And so that's going to give us nitrous oxide gas and H2O gas, and we have to balance this. So for every mole of ammonium nitrate, we're going to form 1 mole of nitrous oxide and 2 moles of gaseous water. 3 moles of gas. Otherwise, it's not balanced, and so we've got to make sure it's balanced. And so your book is going to use this as a mole ratio. And so one way we can do this is that we're going to get a 1 mole of ammonium nitrate produces a total of 3 moles of gas. I mean, it doesn't matter what the gas is. It could be a mixture, it could be pure, you know. But in this case, it's a mixture. And so we could use this as a mole ratio. And so what we can do here is we know the volume of the gas. This is 82.3 liters. And we know the temperature, 447 degrees C. And we know the pressure, 896 torr. So there are different ways we could do this. One, we could use the ideal gas law to figure out the moles of gas. That is, N is equal to P V over RT. Or 2, we can use the liters and the molar volume and then go from this, 82.3 liters of gas, and then calculate the molar volume. The molar volume under these conditions will be RT over P, which is 0.08206 liters times atmosphere over mole Kelvin times T. So 273 plus 447 gives, what was the temperature you got? 710? Is that what you got? 720?
Yeah.
720 Kelvin divided by P. So we have to convert that into atmospheres. 896 torr, 1 atmosphere per 760 torr. And what was the molar volume that you calculated? For this? What was it? 50.1 liters per mole? Okay, thanks. Okay, this is from this just stoichiometry here. And so did you do this 82.3 liters and then you got 1 mole of gas per 50.1 liters of gas? This only works at this temperature and pressure. At other temperatures and pressures, we'll get a different molar volume. And then we use this generic conversion factor here. 1 mole of ammonium nitrate, ammonium's NH4, ammonium nitrate for every 3 moles of gas. And then the molar mass for ammonium nitrate, you look it up or you can calculate it. What did you get for the molar mass of ammonium nitrate? 80.04 grams of ammonium nitrate per mole. of ammonium nitrate. Is that right? Okay. And then you got, what was the number?
43.8.
43.8 grams of ammonium nitrate. All right, that's just taking advantage of the properties of the gases. All the gases, these molar volumes are for any gas. So it could be a pure gas or it could be a gas mixture. It works for any gas. Now, there are three other ways that we could deal with this. The three other ways are dealing with the mixture itself. Over here, we didn't do anything with the mixture. We kind of bypassed the mixture. We said the mixture is going to be a total of 3 moles. It's a 1 to 3 mole ratio. So 1 mole of solid yields 3 moles of gas. Correct? Now, there are 3 ways of handling gas mixtures. And so, from a gas mixture approach, this is what we could do. So we have the nitrous oxide and the water mixture, steam. The first way of dealing with gas mixtures is the mole fraction or the mole percentage. And this is always true. So when we have a mixture like this, it's always going to form in a 1 to 2 mole ratio. So for every nitrous oxide, we get 2 waters. And it can't be anything else because all the water comes from the decomposition of nitrous oxide. We don't have any humidity present. The humidity can change the amount of water vapor in the air. And so let's just say there's no water vapor from humidity. All this water came from the explosion itself. And so that's going to fix the amount of water that we can generate from this. And so if there's no external humidity, then we get the mole fraction. And so the mole fraction of nitrous oxide, N2O, is going to equal this. We have 1 mole of nitrous oxide for every 3 moles of gas. Excuse me. So it's going to be the mole fraction looks like this. The mole fraction, that's over here, is going to be moles of A over total moles. So if I want to convert the mole fraction into mole percent, the mole percent would be 1/3 times 100, which is going to be 33%. So it's 33% nitrous oxide. And then we can do the mole fraction of water. The mole fraction of water, well, there are 2 moles of gaseous water, or water vapor, per 3 moles of gas total. And so that would be the total moles. And so if we were to do this using mole fractions in the mixture, what we could have done is this instead. We could have calculated the total moles of gas based on the P total, V total, and the temperature for the total. And so a setup like this would probably go like something like this. We have a total of 82.3 liters. This would be our V total. And then we'd use the molar volume, which is this. 1 mole of gas for every 50.1 liters. Yeah. And so this gives us the total moles of gas. And then we can convert it either into nitrous oxide or water. We'll go with nitrous oxide, perhaps. So we'll go 1 mole of nitrous oxide for every 3 moles of total gas. And so 1 out of the 3 moles is nitrous oxide. And then we'll convert that into ammonium nitrate. We could have gone to water too. And it's a 1-to-1 mole ratio. So 1 mole of ammonium nitrate for every 1 mole of nitrous oxide. And then we could go to mass of ammonium nitrate using the molar mass, which is what, 80 point whatever. Was it 80.01? And so this is solving it using mole fraction. So what we do is we know the total moles of gas, and then we know that nitrous oxide is 1/3 of the total moles, or we could have gone to water. Water would have been 2/3, but then that would change the mole ratio here if we use water instead. And then we do a mole-to-mole conversion.
I have 80.05. Does anyone else have
80.05? Okay. Let me change that. My pens are running out. All right, so that's mole fraction. Mole fraction is always true. But we can also visualize the problem in terms of not mole fraction, but in terms of volume fraction. Or volume percentage. So in terms of volume percentage, it would look something like this. It would be the volume of A over the total volume would be the volume fraction of A. And so in terms of nitrous oxide here, we would have a volume fraction like this. We'd have 1 liter of nitrous oxide for every, how many liters total? 3 liters total. And so in other words, we have 3 gases occupying it. Well, actually we have 2 gases, but we have twice as much water. And so occupying the space, the nitrous oxide would only occupy 1/3 of the volume. That would be the volume fraction. And water would occupy 2/3 of the volume of this container. And so this would be the volume fraction of nitrous oxide. The volume fraction of water vapor would be 2 liters of water vapor for every 3 liters total. And the volume fraction has to add up to 100%, just like the mole fraction. The mole fraction has to add up to 100% too. So again, 1/3 mole of nitrous plus 2/3 mole water, that's going to give us 3/3 mole total. And the same thing here, if I have 1/3 liters of nitrous and 2/3 liter water, then it's got to add up to 100% in liter. So the other way of solving this particular problem is like this. Instead of using 82.3 liters, I would do it like this. Okay, this is 82.3 liters of total. And out of that total, only 1/3 of that total is nitrous oxide. And so that's 1 liter of nitrous oxide for every 3 liters total. Okay, then I would convert this into moles using the molar volume. What was it, 50.1? I should have erased it. Liters per mole under these temperature and pressure. And so that gives us the moles of nitrous oxide. And then from the moles of nitrous oxide, it's a 1-to-1 mole ratio. 1 mole of ammonium nitrate for every 1 mole of nitrous oxide. I could have gone to water as well. Doesn't really matter. And then convert that, 80.05 grams of ammonium nitrate to moles. From moles of ammonium nitrate. And we're going to get the same answer. You see that? But this is tricky because what's going on with the pressure? So this is what we call Avogadro's law. In Avogadro's law, the volumes are additive. And so for Avogadro's law, we note that V total is equal to the sum of the partial volumes. The sum of the partial volumes is going to equal the volume of the nitrous oxide plus the volume of the water vapor. One-third of the total volume is going to be occupied by the nitrous oxide. 2/3 of the total volume will be occupied by the water vapor. And so the volumes are additive. What about the pressures? And so the weird thing about this is the pressures are not additive. And so the pressure, total pressure, is going to equal the pressure of nitrous oxide, which is equal to the pressure of the water vapor. And so the total pressure is the pressure of the mixture. And so everything has the same pressure, and so we call this constant pressure. And so Avogadro's law is only valid under conditions of constant pressure. Whereas mole fraction is valid at any pressure and any temperature. Constant P and C, actually. The other way of visualizing this mixture is not by Avogadro's law. The other way of visualizing this mixture is by Dalton's law. When we deal with Dalton's law states that, well, actually, we'll look at the pressure fractions here. So the pressure fraction of A is PA over P total. And so we're going to look at the pressure fraction of nitrous oxide. Nitrous oxide will be 1/3 of the total pressure because 1/3 of the collisions will be due to nitrous oxide, 2/3 of the collisions will be due to the water. And so this would be 1, and the pressure, we could use atmospheres or torr. Maybe we'll just use torr in this case, it doesn't matter the units. So 1 torr of nitrous oxide for every 3 torr total. And so 1/3 of the total pressure will be generated by the nitrous oxide. And if we look at the pressure fraction for H2O gas, 2/3 of the total pressure will be due to water. So 2 torr of water vapor colliding for every 3 torr total. So the setup of this is a little different. So when we set this up, we look at the pressure, P total here. And so I'd start off with the pressure of 896 torr total. And I realized that only 1/3 of that pressure is due to the nitrous oxide. And so I'm going to say that only 1/3 of this pressure is due to the nitrous oxide. And that gives me the pressure of the nitrous oxide. Once I have the pressure of the nitrous oxide, then I can do what? Is it time?
Yeah.
Oh, it's a little bit time. All right. All right. So unfortunately, we'll have to continue this next time. Go ahead and turn in your thing.